Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Code execution in the context of artificial intelligence refers to the ability of models or their surrounding infrastructure to invoke scripts, programs, or external tools as part of completing a task. This capability is especially common in plug-in ecosystems, retrieval-augmented systems, or tool-integrated assistants, where the model is expected to not only generate text but also trigger actions in the real world. While powerful, this functionality carries inherent risks. Arbitrary command execution could allow malicious inputs or compromised components to run unintended instructions on the host system. Because AI-generated outputs are not inherently trustworthy, the execution of code based on those outputs must be tightly controlled. Containment becomes a core requirement. Without it, the bridge between generative reasoning and operational tools exposes the entire system to compromise. Code execution thus offers both enormous utility and substantial danger, making safeguards like sandboxing essential. The risks of uncontrolled code execution are varied and severe. Privilege escalation occurs when processes exploit vulnerabilities to gain higher levels of access than intended, threatening the integrity of the host environment. File system tampering allows malicious scripts to alter, delete, or implant harmful data, potentially corrupting both the operating system and business-critical assets. Network exploitation could involve unauthorized connections, port scanning, or lateral movement into other systems, using the execution environment as a beachhead. Data exfiltration is perhaps the most concerning, where sensitive information, whether customer records or proprietary models, can be silently extracted. These risks are amplified in AI contexts, where code may be executed automatically in response to model instructions, leaving limited opportunity for human oversight. Recognizing the scale of these threats is the first step toward designing effective containment strategies. Sandboxing is the primary defense mechanism for safe code execution. A sandbox is an isolated environment in which code can run without direct access to the underlying system. The goal is to contain potential damage. Even if a malicious or buggy process runs, its ability to affect the host is tightly constrained. Sandboxes restrict system resources, ensuring that rogue programs cannot monopolize CPU or memory. They contain malicious activity by walling off file systems and networks, while logging all actions for later review. In this way, sandboxing transforms code execution from an uncontrolled risk into a managed experiment. It does not assume trust. Instead, it limits trust by ensuring that even harmful code remains boxed in, unable to escape or spread. For AI systems, sandboxing is not optional. It is the structural foundation for executing model-driven actions safely. Different types of sandboxes provide varying degrees of isolation. Virtual machines offer strong separation by emulating full operating systems, though at higher resource costs. Containers deliver lighter-weight isolation, using kernel features to limit visibility while sharing the host OS. Language-based interpreters restrict execution to safer subsets of instructions, as seen in restricted Python or JavaScript environments. Hardware enclaves, such as trusted execution environments, provide cryptographic guarantees that code runs securely in protected regions of a processor. Each type offers trade-offs between performance, flexibility, and strength of isolation. Selecting the right approach depends on context. Research environments may prefer lightweight containers, while high-security deployments may rely on full virtualization or hardware-backed enclaves. Understanding these options enables architects to design execution environments that balance efficiency with resilience. Sandbox policies define what code inside the environment can and cannot do. Restricted system calls prevent access to dangerous kernel functions, closing doors to privilege escalation. Controlled memory allocation ensures that processes cannot exhaust resources and cause denial of service conditions. Limited network access blocks unauthorized connections, allowing only approved destinations or none at all. Denial of unsafe operations prevents risky behaviors like arbitrary file writes or spawning unapproved sub-processes. These policies turn the abstract concept of isolation into enforceable rules, reducing the chances of sandbox escape or resource abuse. Well-crafted policies create a least privilege model inside the sandbox itself, ensuring that executed code has just enough permission to function but no more. Such granular control is critical because even within a contained environment, excessive freedom can still lead to harmful outcomes. File system controls further tighten the boundaries of execution environments. Read-only mounts prevent code from altering critical directories, safeguarding both the host and the sandbox's own runtime. Scoped directories limit visibility so that only designated paths are accessible, reducing the risk of sensitive data leakage. Ephemeral storage provides temporary working space that disappears after execution, ensuring that no malicious changes persist across runs. Logging of file access builds accountability, allowing administrators to trace suspicious behaviors such as repeated attempts to open protected files. Together, these measures prevent code from turning the file system into an attack vector. In AI tool use, where models may attempt to write reports, process documents, or interact with structured data, such controls ensure that actions remain bounded, auditable, and reversible. The file system becomes a carefully managed surface rather than an open canvas for exploitation. Network controls inside sandboxes address one of the most dangerous attack surfaces: connectivity. Blocking external connections by default prevents untrusted code from reaching the wider internet, where it could download malware, join command and control networks, or leak sensitive data. Whitelisting destinations allows administrators to permit only necessary endpoints, such as a trusted database or a specific API, minimizing exposure. Rate limiting ensures that even approved connections cannot be abused for denial of service attacks or mass data transfers. Isolation of sensitive endpoints prevents sandboxed code from probing or attacking critical internal services. Together, these measures create a tightly defined perimeter for sandboxed processes, reducing the likelihood that misbehavior spreads beyond the contained environment. In the context of AI tools, where models may call external resources for tasks like data retrieval, these controls provide essential guardrails against unintended or malicious behavior. Execution limits act as safety brakes on sandbox activity. CPU usage restrictions ensure that no single process consumes disproportionate resources, preserving stability for other workloads. Memory ceilings prevent exhaustion of system resources, which could otherwise trigger crashes or performance degradation. Runtime timeouts automatically terminate processes that run longer than expected, limiting opportunities for infinite loops or resource hogging behavior. Process quotas cap the number of concurrent tasks, preventing runaway job creation. These limits transform the sandbox into a predictable environment where resource consumption is bounded and manageable. In practice, execution limits protect not only against malicious exploitation, but also against accidental errors. In AI-driven execution, where instructions may be automatically generated, such safeguards are essential to ensure that even unexpected requests cannot overwhelm the host. Monitoring within sandboxes ensures visibility into what occurs behind isolation walls. Tracing system calls provides detailed records of the operation's code attempts, helping detect both policy violations and subtle exploits. Auditing input and output confirms that data entering and leaving the sandbox follows expectations, ensuring integrity and compliance. Anomaly detection signals can highlight deviations in behavior, such as unusual file access or repeated failed network attempts. Forensic replay allows investigators to reconstruct what happened during execution, aiding in post-incident analysis. Monitoring is not just a secondary layer but a vital element of containment, ensuring that sandboxes are not black boxes where threats can hide. By combining isolation with active oversight, organizations gain both control and clarity, essential qualities in securing AI-driven code execution. Policy enforcement layers create another dimension of defense. Validation before execution checks whether a requested operation is allowed. Filtering unsafe instructions early. Rule-based deny lists identify operations or patterns that are outright prohibited, such as attempts to access sensitive files or run privileged commands. Filtering of requested operations narrows the execution surface, ensuring that only permitted tasks proceed. Fallback safe modes provide continuity by substituting safer defaults rather than failing silently or catastrophically. These enforcement layers ensure that sandboxing is proactive, not just reactive. Instead of waiting for malicious actions to occur, they block dangerous requests before they begin, preventing harm altogether. In AI contexts, where instructions may vary unpredictably, pre-execution validation provides a necessary safeguard against unforeseen or adversarial prompts. Secure plugin execution represents a specialized but critical case of sandboxing. Plugins expand the functionality of AI models, connecting them to external tools, services, or data sources. Without strict controls, however, plugins can become backdoors into the host system. Scope-limited connectors ensure that plugins can only access the specific functions they need, reducing privilege exposure. Strict permissioning defines what each plugin may or may not do, aligning its capabilities with its intended purpose. Continuous monitoring of plugin behavior detects unusual actions, such as repeated failed requests or unexpected data transfers. Revocation mechanisms allow administrators to disable plugins instantly if misuse is detected. These practices transform plugin ecosystems from risky add-ons into manageable, trustworthy components of AI systems, enabling innovation without sacrificing safety. Defense in depth ties all these layers together into a resilient whole. Multiple isolation layers, such as combining containerization with language-level restrictions, ensure that if one barrier is bypassed, others remain. Overlapping controls, such as both network filtering and rate limiting, provide redundancy against persistent attackers. Layered logging captures activity at different levels, ensuring that no single blind spot undermines visibility. Redundancy in enforcement builds resilience, making sandbox escapes significantly more difficult to achieve. Defense in depth reflects the recognition that no single mechanism is perfect. By layering controls, organizations create robust environments where failures are anticipated and contained. In AI-driven execution, where unpredictability is inherent, this redundancy provides confidence that even novel or unforeseen threats will not cascade into systemic compromise. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Failure modes without sandboxing demonstrate why these controls are indispensable. If code is executed in unrestricted environments, the system faces the risk of full compromise. An adversary could install backdoors, tamper with configurations, or take control of administrative accounts. Uncontrolled data exfiltration may allow sensitive information ranging from customer data to intellectual property to be silently siphoned away. Malware could spread laterally, reaching other applications, databases, or even entire networks, transforming a local incident into a systemic breach. Catastrophic outages are another consequence. Poorly constrained processes can crash hosts, corrupt services, or render entire infrastructures inoperable. These outcomes highlight that sandboxing is not a luxury or an optimization. It is the bedrock upon which safe code execution depends. Without it, organizations essentially gamble with their most critical assets every time AI systems invoke external code. Trade-offs in sandboxing must be acknowledged alongside its benefits. Strong isolation mechanisms often introduce performance overhead as emulation or virtualization consumes additional resources. Reduced developer flexibility is another cost, as engineers must work within the constraints of sandbox policies rather than having unrestricted system access. Higher complexity arises when layering multiple sandboxing mechanisms together, requiring skilled management to avoid misconfiguration. Limited functionality may also result, with some operations blocked, even if they are benign in intent. These trade-offs highlight a tension between agility and assurance. Organizations must weigh whether the cost of slightly slower or more constrained execution is acceptable compared to the risk of uncontained compromise. In high-stakes AI environments, the answer is almost always clear. Safety outweighs convenience. The tooling ecosystem for sandboxing is diverse and growing. Container runtimes such as Docker and Kubernetes provide widely used mechanisms for isolating workloads while still supporting scalability. Serverless sandboxes, often offered by cloud providers, allow execution of code snippets with tightly constrained lifetimes and resources. Browser-based execution controls restrict what web-delivered scripts can do, protecting users from malicious or buggy code in client-facing applications. Cloud-native isolation services, such as those built on trusted execution environments, combine hardware-level protections with managed infrastructure, appealing to organizations with stringent compliance needs. Each tool reflects a different approach to achieving the same goal, enabling code to run in a controlled, observable, and minimally risky environment. Selecting and combining the right tools ensures that sandboxing is both effective and aligned with organizational requirements. Alignment with zero-trust principles reinforces the role of sandboxing in secure architectures. Just as zero-trust rejects the assumption of implicit safety in network traffic, sandboxing rejects the assumption of implicit safety in code execution. Every request, every process, and every resource access must be verified and constrained. Verification at each step ensures that execution never exceeds its defined boundaries. Layered authentication mechanisms such as requiring tokens for plug-in access prevent unverified actors from triggering operations. Strong boundaries segment execution from sensitive resources, ensuring that even if malicious code runs, it cannot reach beyond its permitted scope. Sandboxing operationalizes zero trust at the execution layer, turning philosophy into practice. For AI systems, this alignment ensures that untrusted model outputs cannot directly translate into untrusted system actions. Operational best practices strengthen sandbox security beyond technical configuration. Regular patching of runtimes ensures that known vulnerabilities cannot be exploited for escape attempts. Minimizing dependency usage reduces the number of potential entry points, as each library or framework may contain latent flaws. Strict configuration policies provide consistency, preventing gaps that arise from ad hoc setups. Routine penetration testing simulates attacks against the sandbox, validating that isolation mechanisms function as intended under stress. These practices transform sandboxing from a one-time deployment into an ongoing discipline embedded within the organization's security culture. By continually testing, updating, and refining, teams maintain confidence that their sandboxing environments are capable of withstanding real-world threats. Metrics for measuring sandbox effectiveness provide valuable feedback loops. Tracking sandbox escape attempts highlights how often adversaries probe for weaknesses and whether defenses hold. Counting blocked unsafe calls quantifies the success of policy enforcement layers. Monitoring runtime stability ensures that isolation controls are not destabilizing workloads under normal conditions. Assessing resource efficiency clarifies the balance between performance and protection, guiding adjustments to configurations. These metrics transform sandboxing from an opaque barrier into a transparent, improvable system. Organizations that monitor effectiveness continuously are better positioned to adapt, evolve, and maintain confidence in their defenses. Metrics also provide evidence for auditors, regulators, and stakeholders that sandboxing controls are not just theoretical, but demonstrably effective. The strategic relevance of sandboxing lies in its ability to enable safe ecosystems for AI-powered plugins and tools. Without containment, connecting models to external functions would be prohibitively risky, exposing enterprises to unpredictable outcomes. By isolating execution, organizations can confidently allow models to extend their capabilities while knowing that harmful behavior will remain constrained. This makes sandboxing not only a technical safeguard, but also an enabler of innovation. It prevents catastrophic breaches by ensuring that even if malicious instructions are executed, the impact is localized and manageable. It also supports regulatory compliance, demonstrating that sensitive operations occur within tightly controlled boundaries. In effect, sandboxing forms a foundation for secure AI deployment, balancing flexibility with protection in a way that preserves both trust and functionality. Strategic considerations also emphasize resilience. Sandboxing ensures that failures are not systemic but contained, allowing organizations to recover quickly from incidents. In environments where AI systems are entrusted with mission-critical operations, such resilience is essential for maintaining continuity of service. Sandboxing also bolsters trust across ecosystems, giving partners and customers confidence that integrations will not compromise security. For regulators, sandboxing offers demonstrable assurance that code execution risks are being managed responsibly. These broader impacts highlight that sandboxing is not merely a technical mechanism, but a governance instrument, shaping how AI systems interact with their environments and how stakeholders perceive their reliability. Sandboxing further supports layered defense strategies. By combining isolation with strong identity, network, and file system controls, it creates environments where even sophisticated attacks face multiple barriers. Redundancy ensures that the failure of one mechanism does not translate into systemic compromise. This layered approach also aligns with enterprise security frameworks, such as Defense in Depth, which emphasize that no single control can be relied upon absolutely. In AI, where unpredictability is inherent, layering adds assurance that novel exploits or adversarial behaviors will encounter multiple choke points. In practice, sandboxing becomes one layer in a broader security tapestry, supporting but not replacing other essential controls such as gateways, monitoring, and governance. At the enterprise level, sandboxing fosters cultural change by encouraging developers to build with security in mind. Knowing that code will execute in constrained environments forces teams to adopt minimal dependencies, adhere to best practices, and respect resource limits. It reduces complacency by ensuring that unsafe shortcuts cannot be hidden within production workflows. Over time, this creates a virtuous cycle where both security and engineering quality improve in tandem. For AI systems which already challenge organizations with their scale and unpredictability, embedding sandboxing into the culture ensures that experimentation does not come at the expense of safety. This cultural reinforcement makes sandboxing as much about people and process as about technology. In conclusion, code execution is a powerful but risky capability in AI systems, offering opportunities for expanded functionality while opening the door to privilege escalation, tampering, and data leakage. Sandboxing mitigates these risks by isolating environments, restricting system calls, and monitoring every action. Different sandbox types, virtual machines, containers, interpreters, and hardware enclaves, provide options tailored to varied needs, while policies governing file access, networking, and execution ensure tight control. Monitoring, enforcement layers, and defense in depth make containment robust against both accidental errors and deliberate attacks. Though sandboxing introduces trade-offs in performance and complexity, it remains indispensable for safe, compliant, and trustworthy AI operations. Its presence signals to stakeholders that the organization values both innovation and security. As we transition to the next episode on connector and plugin security, the relationship becomes clear. Sandboxing ensures that code execution is safe, but connectors and plugins define the channels through which AI systems interact with external tools and data. Just as sandboxes contain execution, connectors and plugins must be governed to prevent misuse of access and privileges. Together, they represent the dual responsibilities of AI integration, one focused on how instructions are executed, the other on how connections are managed. By understanding sandboxing deeply, you are now prepared to explore how to secure the broader ecosystem of plugins and connectors in the chapters ahead. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.